Global warming has been a major issue for decades. It refers to the long-term rise in the Earth's average temperature, mainly caused by human activities, especially the burning of fossil fuel like coal, oil, and gas. These activities release large amounts of greenhouse gases into the atmosphere, such as carbon dioxide and methane, which trap heat and make the planet warmer. As a result, we're seeing many serious impacts. The ice sheets at the North and South Poles are melting, sea levels are rising, weather patterns are becoming more extreme, and many ecosystems are being disrupted. We often hear about these problems in the news, but today I want to show you how we can use hypothesis testing to statistically test if global temperature have truly changed over time, instead of just assuming it. First of all, what is hypothesis testing? Hypothesis testing is a method that allows us to make a decision based on data rather than just opinions. It's a statistical technique we use to test whether a claim about a population is likely to be true using evidence from a sample. In every hypothesis test, we set up two competing statements. First of all, we have the null hypothesis. This usually claims that there is no effect, no difference, or no change. It's what we assume is true unless proven otherwise. The alternative hypothesis. This suggests that there is an effect, a difference, or a real change. Once the hypotheses are defined, we collect data from two or more groups to test them. This data should be representative and unbiased, and it can come from real-world observations, experiments, or simulations. After gathering your data, you run a statistical test. There are a variety of statistical tests available, like the regression, comparison, or the correlation. All statistical tests are essentially based on one idea, comparing within group variance and between group variance. Within group variance tells us how spread out the values are inside each group, and between group variance tell us how different the groups are from each other. If the between group variance is large, meaning there is little overlap between groups, your test will give you a low p-value. That means the difference between groups is likely real, not due to the chance, but within group variance is high and between group variance is small, the groups likely overlap a lot. In that case, your statistical test will return a high p-value, suggesting any difference you observe might be due to random variation. Once you have performed the statistical test, the final step is to interpret the result, and the key to this is understanding the p-value. The p-value tells you how likely it is to get your observed result or something more extreme. If the null hypothesis were true, here's how to interpret it. If the p-value is less than 0.05, the most common threshold, you reject the null hypothesis. That means your result is statistically significant and there is strong evidence that a real effect or difference exists. If the p-value is greater than 0.05, you fail to reject the null hypothesis. This doesn't mean the null is true. It just means that the evidence isn't strong enough to prove a difference. In my first example, I wanted to test whether there is a significant correlation between atmospheric CO2 levels and global temperature. This question is at the heart of climate science. We often hear that rising CO2 is linked to global warming, but can we prove that statistically? Well, I will show you how to do it in Excel and follow the steps that I have present. First step is to state the hypothesis. The null hypothesis is there is no correlation between CO2 levels and global temperature. And the alternative hypothesis is there is a correlation between CO2 levels and global temperature. Now here I have a data set which I collected from NASA I will perform the statistical test in Excel. First, I will calculate the correlation to see the relationship between these two datasets, the temperature dataset and the CO2 dataset. First, we click the data and goes to data analysis. We have the correlation and the input range. We will input this and labels in first row and click OK. Here is the correlation. As we can see that the correlation is really close to 1, around 0.93, which indicates a close linear relationship. And yeah, I can use this. And now I'm going to perform a regression analysis using the data analysis toolpath. Now we also click in the data analysis, choose the regression, click OK, and input the y range and input the x range and click the confidence level at the 95%. Now we have the answer. What we have to look at is the significant F, as I have highlighted, and or we can see it at the p-value for the x variable here. So back to the hypothesis. Because the p-value was smaller than 0.5, I rejected the null hypothesis. So in conclusion, there is statistically significant evidence that CO2 levels and global temperature are correlated. This confirms that climate scientists have been saying as CO2 rises, so does global temperature. Example number 2. I have a question. Have global temperatures increased since CO2 emissions surpassed 30,000 million tons a year? I used the same data sets as the example number 1. First of all, I'm going to state the hypothesis. We got the null hypothesis is there is no increase in temperature after CO2 emissions exceeded 30,000 million tons a year. The alternative hypothesis is temperatures are higher after CO2 exceeded 30,000 million tons a year. Well, for this example, first I'm going to find the point where the CO2 emission is below 30,000 is from 1973 to 2005, and the emission exceeded 30,000 when after 2005. And now I'm going to perform a t-test using a t-test formula. The first array is going to be from C2 to C34. Second array is from C35 to C52. And we want to perform the one-tail test. And the type is going to be unequal variance because as you can see that there are a lot more years below the 30,000 million tons a year than the surpassed one. After I used the test, here's the formula, And here is the answer for the t-test, and it's way below the 0.5. So say that the temperatures are higher after CO2 exceeded 30,000 million tons a year.